Okay, so the training is finished now. It actually went fairly quickly because unlike when we were doing it before, where every time the data set had to compute the MFCC, that was a bottleneck there. Here it actually goes straight through the GPU with the layers, so our drop-in replacement is actually much faster. And if we were just going to look at the training accuracy, it looks like it does amazing. It looks like it gets it 100%. But there's a bit of a problem. It is not doing as well in the test set. So let's look at the plot over time. So we see actually that it saturates in the train set, and it also saturates in the test set, but lower. So this is a classic case of overfitting. What we've managed to do is do extremely well in our training set, but our model was so complex that we actually kind of just memorized those examples and we did not generalize to the test set. So I'll explain how to mitigate that in a moment, but let's just, so the test set, I mean, it's not terrible. But if we go and actually try to look at the parameters, so I wrote some code here to plot what kernels it learned. I don't know, each of the kernels looks kind of just like noise. So I'm not really sure how much I learned here. I mean, I see like maybe a little bit of structure, some repetitions. I mean, we're kind of expecting to see things that look like, you know, sines and cosines, or maybe these kind of Gabor cosines that I was showing. You know, to do something like the MSCC, but we're not really seeing very clean examples here. So the fact that the kernels are a little bit noisy, although I don't know, I'm just kind of seeing some oscillations, but kernels are a little bit noisy, and I see this gap here, means that there's overfitting, and I'm going to need to do something to address that. And so there's a few strategies to address overfitting. You either, I mean, they kind of fall into two categories. So one strategy, okay, so maybe I'll save this figure for posterity real quick, and I'll include that in the notes. But so there's two strategies to fight overfitting. So two strategies to fight overfitting, two general strategies. Number one is increase the complexity of your training data. So we can either, I mean, we can get more training data, which I could here actually because I'm not using all of it. So that's one way to deal with it, so get more data. But another way to deal with it is to do something called data augmentation. So this is to take the existing data and instead of returning it directly in the data set, do some transformation to it that makes sense. So, you know, we would, instead of returning the instrument directly, we would return a pitch shifted version of it, or maybe we would crop it a little bit, just something to make the data a little bit different. Actually here I don't want to crop it because I kind of like the fact that they're all 32,000 samples. I'll explain an idea for data augmentation in a moment, but it's just, you know, it's TLDR. It's taking the data we have and like sort of making new fake examples based on it, but that are based on the real data. Okay, so that's one thing we can do. The other thing we can do is regularize the model. So somehow simplify it. So you can, or I guess I should say regularize or simplify the model. So you could say, you know, try to use fewer parameters, or use the same number of parameters, but add a regularization term, which is something to sort of, you know, kind of control the weights a little bit. So maybe, you know, a penalty for the sum of squares of the weight, all of the parameters or something, of squares of all weights. You could also do something called dropout, where you randomly zero out outputs after a particular layer. And so this is kind of like making the network a little bit dumber. So it turns out, actually, I mean, you know, the network is complex enough to perfectly learn the training set, and that's maybe not a good thing. It's actually okay to make the model a little bit dumber. So maybe it doesn't reach 100% accuracy on the train set, but actually the test set, it kind of closes the gap between the two. That would actually be a desirable thing. It's okay to make the model a little bit less complex somehow in order to do that. So those are the two kind of main families of techniques to fight overfitting, and this is definitely much more of an art than a science at this point with how complicated neural networks have gotten. But actually, I was playing around with this before, and I found something, a data augmentation technique that worked pretty well. So let me explain what it is. And to do that, maybe I'll just take out a little audio example and show you how I would transform it into a very similar audio example, but that's different enough that it actually enriches the data. So if I were to, okay, so I have my data that I've loaded here. If I were to take out, let's say the first audio sample. So I'll say maybe data train 00, just to check it here. Okay, I should actually flatten this as well. So I'll say .view. Okay, and so all right, so that's that. I don't know. I'm more comfortable in NumPy, so let me just switch there real quick. So let's say x dot NumPy. Okay, so that all works. And so just to listen to it, let's see what does it actually sound like. Okay, that's not a very exciting example. Maybe I'll jump forward a little bit to this example. Wow, that was interesting. Pretty low pitch there. Okay, I'm gonna stick with that one. So what I can do here is actually warp the audio slightly in time. So I'm not going to take the examples exactly where they are in time. Instead, what I'm going to do is resample them a little bit in a way that you probably wouldn't even notice the difference, but that actually makes all the difference when we go to train. So okay, so here's what I'm going to do. I'm going to create something called a reparameterization function. So I'll say in space from 0 to 1, I want as many samples as there are in X, same number of samples. I'm going to raise this to the, let's say 1.1 power, and then I will multiply this by the length of X minus 1. Okay, what the heck did I just do? So if I plot this, what I'm going to be looking at here is new sample index and old sample index. And so it's what I'm going to do is actually make it slow down a little bit at the beginning, but then speed up towards the end. And so what I'll do is I will use this interpolate function. So I'll say maybe x warp is equal to mp.interp. So I want to sample at these indices, and here's the original thing. I meant to say interpolate. Interpolate. No, actually it was interp. Okay, there we go. So let's listen. Versus this. So maybe it's a little bit extreme. Maybe we'll go down a little bit. Let's say 1.01. Okay. Versus. So it starts off just a little bit low. So it's slightly different data. And so maybe what I'll do is I'll choose like a random number, maybe between 0.99 and 1.01. So this will do the opposite. This will go a little bit faster in the beginning and slow down towards the end. As we hear, the pitch is a little bit higher in the beginning. All right, so what I'll do is I'll just kind of put some of this code into the data loader here. I'm going to pass a parameter to the constructor called augment. It'll be false by default, but I'll say, okay, augment. If true, do data augmentation when accessing an item. So I will say self.augment equals augment. So I'll store that as a member variable. And then, okay, so if I'm choosing to augment, then I will do this kind of thing. So I'll raise this. Okay, so the power I'm going to make be a random number between 0.99 and 1.01. Actually, let me see if that works. mp.random.rand 0.99 1.01. No. So I'm going to have to do, okay, an easy way to do it would just be generate a random number times 0.02 plus 0.99. Okay, so that'll give me a random number between 0.99 and 1.01. And so I will raise to that power. And I don't need to plot all this stuff, but I will resample X here before I pass it along. Okay, so I've changed my data loader to do data augmentation. What I should do then is say, okay, I don't want data augmentation on the test set. I don't need it. I'm going to keep the test set it is. But I will enrich the training set by turning data augmentation on. So I guess I'll just say true here. So let me reload that. And then I will just test this real quick. It says array uses indices. Oh, I shouldn't reuse this name here. Let me call this something different. I'll just call it I. So yeah, that should be okay. I'll try again loading some audio from the train set. And every time it should come out a little bit different, because I'm not seeding the random number generator. So every time it's just a little bit different. So that enriches the training set. Okay, cool. So let me go ahead and run through this again, and I'll let you know how it goes. Okay, so I actually stopped the training a little bit early because I could see that the training accuracy was starting to pull away from the test accuracy. So the test accuracy was only seeing marginal improvements, whereas the training accuracy was still going up. So that is actually another strategy to fight overfitting, which you can do. I'll put it along with the list of the other things. To regularize the model, you can do early stopping. So, when the train set accuracy starts to pull away from the test set accuracy, stop training. Because we know we're just going to start to memorize things in the training set at that point, and that's not particularly helpful. But actually, I did quite a lot better this time, and so I got up to about 95% accuracy on the test set, and so yeah, the confusion matrix looks way better. There's not a single, well, okay, except for read acoustic, every class I'm doing above 90% at least accuracy. That's great. And when I plot the coefficients of each kernel that I learned, I see things that look a little bit more like some of the examples that I was training on. So here, this is a little bit more like one of those Gabor cosines, and I see another one here. So like this one picks out a particular band of frequencies. This one picks out a different band of frequencies. They're noisy, but they're definitely more recognizable than they were before. Oh, here's a particularly nice one. You can see it almost picks out like a rectangular band in frequencies there. So we managed to learn something that it wasn't the Mel space thing exactly, but it was, I can definitely see it picking up a different band. So that band is definitely lower frequency than this band here. So cool. So it learned that all on its own. It was a little bit more complicated. We had to do some data augmentation for this to work. We had to use a convolutional layer. But we're starting to build up in complexity now. All right. So I'll have a couple questions to make sure this made sense, and then we'll talk about some more things in class.